If, say for example, like t is equal to time spent inside d, not the entire time. So for example, if time is spent inside d in one revolution, like in this over here, this is 1d, right? So what is the revolution happening? This is half the revolution. So a particle from this particular point, it will take the time t to go at this particular point. Now again, the same time or t will be for this particular point to this particular point coming off, right? Now well, you may ask me that why have I made this particular semicircle bigger than this, and why subsequently I made each of the semicircle bigger than the previous semicircles. Well, to understand it, we are now going to take the help of this force and the Lorentz magnetic force. Now, as per the Lorentz magnetic force, it says that BQV, or the velocity with which this proton or deuteron is moving, and the charge of this proton or deuteron multiplied by B, this is the B going inside, right, this paper, or going away from the radio. Now this is produced by highly powerful electromagnets, right? So BQV sine theta will be simply equal to this force of mv square by r, because this r over here, this is revolving. So this will be mv square divided by r. Now say for example, this is the first r. We take it as r1, right? Now over here sine theta, closely observe the sine theta. This theta was for Lorentz force, the angle between this B and V, right? If you could recall that was Q, the charge, multiplied by the cross product of V and B. Now the velocity is in this direction, in this plane, but the B is just perpendicular to the plane. So the angle between V and B is simply equals to 90 degree. So sine of 90 or sine of pi by 2 will simply be equal to 1. So we can say over here that BQV now will be equals to mv square divided by r, right? So over here see that V is being cancelled out, leaving only one V on the right hand side, which means now that V will be equals to, if we perform the cross multiplication, that will be BQR1 divided by M, where M is the mass of the proton or the deuteron, right? So we have reached what one of the expression of the velocity. Now say for example, if we wished, like this was one semicircle, and if you ask that to make this semicircle of the same radius, if we wish to make it, this would have been the case like this, of same radius, right? But observe, with the same radius, if the radius is being kept same as R1, the Q would not change, because whatever you perform in these certain circumstances, the charge is not going to same, and with the help of these powerful electromagnets, we are keeping an uniform B, right? So we can see that this B is not going to change, Q is not going to change, and as per consideration, if you ask me to keep the R same, then R will not be changed again, mass will not be changed again, which means that the velocity will not change. It will remain the same. Okay, no problem. But we need to see that is the velocity remaining the same or constant. Let us take a look. This has undergone a half revolution. After that, as being the positive particle, when it is at this position, it sees this one as being the negative plate. So it will be attracted, which means the velocity will increase. Now wait. If the velocity increases over here, how could we say over here that the velocity will remain constant? Then obviously something has to change out of this. If the velocity over here, as we see, it increases, then obviously either we have to increase B, Q, R, or we have to decrease the mass. Mass is not going to decrease. Yes, there is a limitation of cyclotron, but we shall be discussing later. But for the timing, mass is not going to increase, or say it is not going to change. B obviously is not going to change. Q will remain constant. So the only thing it need to change is the R. And that is the reason why we are seeing that over here the radius is increasing. Right? Now there is another concept. T is the amount of time spent inside 1D. This will revolve in, say for example, if the T is 5 seconds, this revolution shall take 5 seconds. Likewise, this revolution shall also take 5 seconds, and likewise this particular bigger revolution shall also take 5 seconds, not more or not less than that. Because likewise we have set the oscillator. Otherwise, say for example, if it takes over here 7 seconds, it will come outside, and say for example it takes for example so 10 seconds, it will come outside and it will see the positive, the negative plate as this one only. So it will just come to rest over there. It won't be attracted. So the time period or the time spent in 1/2 revolution will be the same. And as we could see that if over here the radius is going to increase, which means the distance to be covered is increasing, and the time is kept as constant, so obviously the velocity needs to increase. See in this equation, if time is constant but distance to be covered is increasing, so obviously velocity has to increase. And why the velocity is increasing? Because we see that there is a force of attraction as well as a force of repulsion, right? So now we could understand that this green line, this would not be the path of this particular cyclotron, of this, let's say, the proton or the deuteron. Now we wish to find out that what would be the time spent inside 1D if the velocity is recorded as like this. Okay, we know from this formula that V multiplied by the time taken, we could write it as that V multiplied by the time taken is simply equals to the distance covered. Now what is the distance being covered every time? Say for example in this R1 radius, yes, the perimeter of this semicircle, right? So it will be simply equals to pi R1. So the distance is covered is equals to pi R1. So the time actually is pi r1 divided by this velocity. And what is velocity? We can replace this term. So if being replaced the velocity, it will be b q r1 divided by m, which means that m will go in the numerator side. Now closely observe that this r1 will cancel out this r1, leaving only the expression of t as pi m divided by bq, right? So we have got the expression for this time, which is spent inside 1d. Now minutely observe this expression. Nowhere it has gone to relate with any radius. Is it having any radius? R1 or R2 or R3? No. And that is the reason why, irrespective of the bigger like semicircle or the smallest semicircle, this t is going to be constant for every case, because pi is a constant, m is the mass of the proton or the neutron, it would not change, b is the uniform magnetic field, and q as being the charge, it is not going to change, right? Now we have done all these things. Now we want to find out that what would be the frequency of this oscillator, because we have to set the frequency of the oscillator as such, right? So for that reason we have to first of all understand the behavior of an oscillator. So the behavior of an oscillator, we could see it as such that if we make, say for example, the behavior of the oscillator will be like this. See, this red part indicates that it is on, actually, say for example, this red part is the positive part and this green part is the negative part. Now what will happen is that until and unless the oscillator actually changes its direction or changes totally to be out phase, this G will remain to be positive. But as soon as the oscillator will enter over here, this G will become negative now and this will be positive. So if we relate this one with this G and this one with this G, so we can find out that for this part of the oscillator, this will remain positive, and for this part, this G will remain as negative. And likewise, as the oscillator is being connected with both the D's, the opposite shall happen on the other D, right? Now, if the entire time period of this kind of wave is T, capital T, then for how much time actually this half revolution is taking place? Yes, the half revolution is taking place for that time only when it is, say for example, this was positive, it entered into the negative now. So this will remain over here, and when it will be just on the verge to exit, it will see that it has changed, which means this has changed. So inside this, what was the time? This was small t. So this part will simply be small t, and again when it will go inside, as we know that the small t is not going to change, so again over at this part there will be small t, right? Again after the time small t, this will take as positive, it will go like this will be positive, and again after time t, this will be positive. right? So from this thing we can observe that basically capital T is equal to twice of the small t, right? So we can say over here that T basically is equal to 2 times of small t, which indicates that T is equals to the time period of this oscillator wave is basically equals to 2 pi m divided by BQ, right? And as we know that the frequency of this waveform is basically equals to 1 divided by the time period, thus now we can say that the F is equals to just the reciprocal of this time, which means BQ divided by 2 pi m, right? So now also we have got that what should be the frequency of this oscillator, and this frequency of this oscillator basically depends upon this B, which has been produced by the electromagnet, the Q of the proton or the deuteron, 2 pi as being a constant, and what is the mass of this neutron or deuteron, right? Sorry, the proton and the deuteron, because the neutrons are not going to be over here. As we said that neutrons are basically, they have got no charge, so if we keep over here and do positive, negative, negative, positive, nothing is going to attract or repel that. So either proton, deuteron or electron, but we are not going to use electron in many of the cases because its mass is very negligible. And now here comes the actual concept that why we do not use electrons, right? This cyclotron is a basic device which is used in order to accelerate the, say for example, particles. But why do we need to accelerate the particle? Because we basically want that the final, when it is going out due to the deflective plate, to hit a target, at that time its kinetic energy must be at its peak, right? And if the kinetic energy is at its peak value, then at that particular point of time, if we do observe that kinetic energy is equals to 1 by 2 mv square so we can now state as this V to be the maximum, then only the kinetic energy that will be produced will be maximum, right? And we know that the value of V, this is the maximum over here, if only the radius is being kept as maximum, right? So the maximum kinetic energy, it will simply be equals to 1 divided by 2 mass multiplied by, this is V square, so V square Q square are V square Q square R max square, because if the R, it is the greatest or the largest value, then only the V will be having the largest or the maximum value, divided by m square. Now as we could see that this m will be cancelling out the denominator, leaving only one m in the denominator. So we can write that the maximum kinetic energy is simply equals to B square Q square R max square divided by 2m. This is the kinetic energy which has been for this particular, say, proton or deuteron, right? Now, say for example, this is hitting a target. Now, our main question is that what the target is. Where is its application? Where is the application of the cyclotron? The cyclotron are used in the various applications related to nuclear physics, right? And also they are also used in, say, nuclear researches, and also they are used for cancer treatment in order such that they could penetrate the body, because they are very fast moving particle and they are small even. They could penetrate the body and they could be used in killing the germ cells so that the germ actually does not infect the other cells which is nearby. Now there is a major limitation of a cyclotron. If we could recollect about the relativistic theory given by Albert Einstein, we could observe that in his famous law, Einstein did mention that the mass of any particle actually do change with respect to this equation. Right? Where m naught is basically the original mass of the particle. Right? So for example, the original mass is equals to, say, like only 2 grams. Let us take it for the time being. So that is 2 gram. And the V that is being produced, because over here every now and then it is increasing, the V is increasing, the V maximum. If, say, for example, like say it increased as such that it is V is equals to C by 2. At that point of time we will see that there will be a change over here. If V increases, then obviously the denominator is bound to change, and if the denominator is changing, which means that it is actually m naught divided by something is changing, which means that now we have a new mass. But if you observe closely in all the relations we mentioned, the m, this m, this m, or say for example the maximum kinetic energy, this as m, we have treated that this mass as constant, right? Obviously, like how to treat this mass, this changing mass is not inside the scope of the study of this cyclotron, but for the reference it may be noted that to remove these issues with related like this, the mass is changing, the synchrocyclotrons or the isosynchrocyclotrons are being used, right? So this is all about cyclotron. So I hope you have enjoyed this very famous thing which has actually changed the life of the physics. Thank you.